Currently, he's software engineer at Nefeli Networks. He graduated from UC Berkeley, and he was advised by Professor Scott Schenker. And he's going to start as an assistant professor of CS at NYU's Curran Institute. And he's going to talk about SDN distributed or SDN controllers.
Thanks, Maria. So, if any of you were at NSDI, the slides are from NSDI, so this might be boring. I apologize in advance. So I'm going to talk about coordination in the context of SDN, software-defined networking controllers. So to start with, to make sure we all agree on definitions and everything else. Oh, also, you can interrupt me whenever you have questions or whatever. So to start with and make sure we agree on definitions and such, and make sure that my computer is actually working, I'm going to start by defining what I mean by software-defined networks here. So I'm basically looking at networks. So there are switches and they forward packets. But what makes them software-defined in this particular case is that there is a centralized controller, and how it's implemented is what we'll be discussing. But this controller is responsible for computing rules that the switches use when forwarding packets. And the rules themselves depend on two things: policy, which is an amorphous blob that a network operator is giving the controller, and network state. And so the policy here defines what sets of paths are acceptable. So as a packet is traversing this network, where can it go, where can it not go, should it follow shortest paths, etc. While network state is sort of telling you what is the state of the network, what switches are up, what links have failed, what choices can the controller make. So given this definition, the question that started this entire area a long time ago was, how do we build controllers? So one of the simplest ways to do this is what I would call a single image controller. This is not a common term. This is just something we're defining as such, which is a controller that runs on a single server. And if you worked on SDN in the early days, things like Knox, Box, Roux, and a bunch of these single image controllers were very popular. So how do single image controllers work? Well, they observe a sequence of events from the network. And what I mean by observe is that switches send them a sequence of events indicating what is happening. And they can use these events to compute network state. So what this means is that a switch will send an event saying, hey, a link has failed, and the controller can then update a graph of what the network looks like by removing that link. Similarly, if it gets an event that says a link has now been added, it can augment that graph by adding a link when necessary. And we have applications, which I'm just defining as something that runs on top of the SDN controller and actually takes the policy and computes what paths are used. And these applications essentially react to these events by receiving these events, augmenting the graph, and computing the new set of rules that they need to have. Now, to make sure that, so one concern here is that an event might get lost, or you might get reordering of events from the same switch. So for example, if a link fails on a switch and then comes back up, you'd like that to not be reversed. And you'd also like to not lose those events. So the way we get around this is we send event updates over a reliable ordered channel, which is provided by TCP. The thing, though, is that despite this, events from different channels, from different switches, can get reordered. There's no ordering guarantees across switches. That's a physical impossibility in this particular system. So even though in actual time switch A might have had an event happen before switch B, the controller might observe them in the opposite order. And similarly, updates sent from the controller to the switches can be applied in arbitrary order. So even if the controller computes an update for switch A before it does one for switch B, or sorry, the other way around, they might receive them in the opposite order. Good so far? Okay.
That's what could be worse than that events within a switch can be reordered. Also.
No, so I'm assuming TCP. I'm assuming a stable connection. So no, there is no, we are, for the purposes of this talk, we are assuming no reordering within a switch.
I mean, that's like I worked at Arista, and everything in the chassis switch is eventually consistent. So our order, it's not entirely clear what order means.
Sure. So a lot of this talk is about the fact that we don't know what ordering means. For the purposes of this talk, you can think of the switch as one monolithic entity. When the switch, so it's an abstraction, I'm just treating the switch as an entity. When the switch sends a message, or if the switch sends to the external world messages in some order, we assume that the switch wanted them in that order. The fact that internally the switch might have reordered various events in various ways, it's fine. We allow that, but that's not our concern here. Okay, so one question that comes up is, how should you handle controller failures? How should you scale controllers and do other things? So remember, everything I talked about was running on a single server. That server fails, your network topples over, and you're sad. So the way people address this, actually very early on, in fact, one of the first SDN controller papers ever was about this topic, was you can move to distributed controllers. So now the question becomes, how should you build a distributed controller? Okay, so is this any harder? And if so, why? So the problem is that now we not only have two sources of events, but we also have two different observers of those events if you have a system with two controllers. And what this means is that controllers might themselves disagree on the order in which events happen, on which they observe events in the network. So in this case, you can see controller 1 thinks event E1 happened before event E0, while controller 2 thinks the opposite. So the problem, though, is that if these controllers happen to disagree on what the final state of the network is, you might get all sorts of weird behavior. You might get dynamics where the network is an incorrect state. It can't agree on what the final set rules are. So we want to make sure that things converge despite this reordering. So canonically, there are 2 ways you can handle this. The first is you can build algorithms that are correct despite reordering. Who cares what order events are received in? You just need some local properties, build algorithms that are fine with that. Life is good. The second is you can use mechanisms that allow all of the controllers to agree on the ordering and on the order in which events are happening. I'll show an example of this in a second. Now, the trade-off here is the following. This restricts the class of algorithms you're allowed to use. You must use algorithms that are independent of the event order. This allows you to use all of these algorithms, but potentially comes with other costs, which we'll be talking about. So as a result, almost all of the distributed controllers that exist right now have relied on ordering mechanisms for generality. So given this, how do we actually establish event order in today's controllers? So the canonical solution to this has been consensus. And for the purposes of this talk, we're going to treat consensus like a black box that I will slowly add some details to. If you're looking for a full explanation of something, of a consensus protocol like Raft, Zab, or Paxos, John Osterhout has a series of videos on this. Maybe you should go watch those. They're great. Okay, so the entire idea behind consensus is it's a protocol that allows different participants in a distributed system to reach agreement on something. In this particular case, we rely on consensus to enable controllers to reach agreement on what order events happened in. So the way this works is when controllers receive events, they send it over to the consensus oracle. The consensus oracle does some magic, and based on this magic, it decides on an ordering, and it sends them back something saying, hello, this is the ordering in which you shall deliver the events to the application. The application on each of these controllers always sees events in the same order. And as a result, each application can use the same algorithms it was using in the single image case, and assuming that the algorithm is deterministic, which is something we need just because we're in this distributed setting, they will both get to the same conclusion. And this particular framework that I described is called replicated state machines. It's a very common framework in building distributed systems and building fault tolerance for distributed systems. And this is the model that was adopted by Onyx, which is an OSDI paper from 2010 or so, and Omos, which is a current open source controller, and from other controllers, both open source and closed source, that are distributed. So just to drive this home, let's briefly look at how consensus ends up being can be implemented in this case. So we're going to look at algorithms like Zab, Raft, or Multipaxos, which are which use leaders to speed up the actual process. So the way it works is at the beginning of time, the mechanism appoints a leader. In this case, controller 1 has that crown on it. The leader is responsible for receiving all network events. And what this means is we are now back in sort of the single event land. The leader's order is the order that we shall all follow. Upon receiving these events, the leader needs to replicate these events to a set of other controllers. And in particular, it must wait for a quorum of controllers to confirm replication. Now, a quorum, I'm not going to define what a quorum is here. In many common cases, people think it is 1/2 of the controllers plus 1. In reality, we just need some intersection properties, so you don't need to actually, you can set the number arbitrarily as long as you deal correctly with failures, but we won't go into that here. But the basic idea is now that once you have got a confirmation from a quorum, the leader can make whatever decision it wants and go along its merry way. Now, the only concern is what happens if the leader fails, because remember, the reason we started replicating, among other things, was to get fault tolerance. If the leader fails, the protocol needs to appoint a new leader, but the protocol must have mechanisms that make sure that any new leader that it appoints has as much information as the previous leader did. So as a result, you can make sure that you never lose this ordering information that you've decided on before. And because of this, and again, assuming deterministic algorithms, you can have the controller reconstruct the state by replaying these events. So this is a mechanism that has been used. It's fairly successful. It's fairly simple to build because there is software available that will implement consensus for you. But there are some limitations. So the first one is fault tolerance. So if you have any case in which the control network partitions, or if you're building a wide area SDN network, and hence the control and the data network are the same, the network partitions, then at least one of the partitions will stop making progress. And the reason for this is very simple. So remember that intersection property that I was trying to ensure. To make sure that the intersection property works, one of the partitions must not have enough participants to actually be able to elect a new leader. Otherwise, you'd violate the quorum properties that I defined earlier. The other problem is that the scalability it's not very scalable. As you increase the number of controllers, you increase quorum size. As you increase quorum size, the exact number of controllers that you must wait to respond grows. And you start running into this problem where the tail of the last quorum response that you're getting is going to be bad. And finally, in general, we have strong theoretical results from the 80s, in particular from the FLP results, that talk about the fact that bounding the total amount of time taken for consensus is an impossible task. And as a result, the performance that we see is very good when your network is behaving well, but is very sensitive to things like network losses, additional latency for quorum messages, or anything like that. So when your network when your control network has bad dynamics or is slow, you will start seeing things slow down, which might be a bad time for things to slow down, because that's probably exactly when you need the network to respond. Yes?
But partition, you partition among the consensus participants or the actual node?
I explicitly here mean a partition in the control network. But one of the things that, at least in this work and in general, that I've been very interested in is applying things like software-defined networking to wide area networks. In wide area networks, it's not clear that you can easily have a distinction between the actual data network and the control network. The idea that you should lay out two networks to connect or to build a network is an insane idea, especially when you go to large enough distances. So if you squint at it, it comes down to the same thing again. Okay.
Yeah, it seems like this is much more likely to happen in a WAN where you only have a single fiber that all of a sudden its properties gotten bad, so it's all of a sudden lossy or slow or whatever, or not available. Rather than
even if you're building a WAN, if you don't want to spend the additional money to build a control network, which still seems like a very strange choice that people make, there is value to having in-band networks. And the
Well,
moment
I was
you're-
saying in a LAN, you don't have to worry about losing usually you don't have to worry about losing your only connectivity. Like in a cloud or in a local cluster, there's extremely rich, like you probably have like full mesh connectivity for something. So if one link fails or gets bad, you just trim it. So in LAN, you may only have one fiber on your transatlantic cable or something, in this case.
Sure.
If it goes south, you're kind of out of luck.
Sure. Okay, so given this, the question we wanted to ask in this paper is consensus required? So this partially came out of seeing a whole bunch of work that I'll mention towards the end, some of the related work that went on to have stronger and stronger consistency requirements. So far what I've talked about is just build a replicated state machine. There's actual work out that talks about require exactly once consistency for building SDN controllers. Okay, that's sort of crazy. So the question was, is consensus required? So let's ask ourselves, why did we originally think consensus was required? Well, the reason is that, remember, the model that I showed was that the controllers sit around, they receive events from the network. These events, if lost, might be lost forever. And they use these events to compute what the topology of the network is, what the forwarding tables are, what is the current network state. But what this means is that you cannot lose network state, and RSMs are there to make sure that once you've computed this network state, everyone will come back to the same network state, you're not going to lose it. And this is basically the exact reason why RSMs are popular in other domains. If you're building a distributed key value store and it has consistency, you, at the end of the day, build RSMs exactly for this. So the problem, though, is at the end of the day, a controller is controlling a network. There is no reason why it needs to remember the network state. You could always go query the network to figure out what the state of the network is. You could ask the network, hey, what links are up? What are your current forwarding tables? Can you tell me how things are looking? And based on that, come up with get back the same network state that you had before. And this observation means that if we go to such a network, it's completely safe to lose network state. You don't need to have it around. You can just get rid of it. So if you have this mechanism, an alternative view of how one might build something like an SDN controller is you have agreement only on policy. So remember, policy comes from humans. Humans change slowly, or at least in they take seconds to make changes as opposed to making it constantly. And assuming that everyone agrees on policy, each controller periodically and completely independently goes and asks the network, hey, can you tell me what your current state is? Based on this state and on the policy that they all agree on, it computes a set of updates. And then it installs updates on the network. And assuming quiescence, by which I mean assuming that no new network events are happening, as long as these controllers eventually agree on the state of the network, they will agree on the set of rules that they compute, and we will reach convergence. So this is basically the one-line summary of what SCL is. We're basically done at this point.
Excuse me.
Yes.
This slide. So the number one sends they receive the same, let's say, the current status individually, right?
Yes.
So that's always the same?
No, but that's why I had to make this. That's why I had to make this quiescence assumption. So basically, it depends on what is included in the state, which is a good question. So imagine that the state just included topology information. So now, if your network topology is changing constantly, you're screwed. These things will never agree on the state that they get back. But let us assume that we want to use a good network. So we want a network where, in general, the network does not have dynamics for a very long time, and the network is mostly stable. So if links are mostly stable, and you set the sampling interval for these controllers such that they are likely to sample during the same stable period, at that point, yes, the topology is the same. So you are correct. The topology is not guaranteed to be the same all the time. Our entire system only provides eventual guarantees on convergence. It does not provide any instantaneous guarantees on convergence.
Okay, thank you. Yeah.
So what happens in this context when one of the controllers goes down?
Nothing. So all controllers constantly work on the entire network.
Oh, so they're not querying partial network tables. bring the entire network state.
Yep.
Oh, really? Wow.
Oh, that's okay, because in the figure, it seems like you're only querying portion.
Sorry,
Okay, no, that makes sense. So now you don't worry about multiple.
No, and so in general, to your question about like this, so I will explain why we didn't find this to be a particular problem in our case, but there are other proposals, including an old one from Toronto called Hyperflow, that also looked at partitioning the network, so using both sharding and replication to get fault tolerance.
Right.
The problem there was that they were basically getting fault tolerance on each shard, and then if you put enough controllers there, you can make sure that as long as each shard is alive, the overall thing will continue to be alive. So we could also go to that sort of a technical system, but here we chose the simplest, dumbest solution possible, which was constantly everyone queries for everything. Yes.
When you say, excuse me, when you say policy, what does that mean? Is that switch level policy? Is that network-wide policy? Is it,
so what the policy means is sort of embodied in the application you choose. So if you pick an application that that only requires network-wide policy and can use network-wide policy to compute switch configuration, then that's what I mean. If you have an application that blindly takes switch level policy and transmits it down to the switches, then that's what I mean. Yes.
If I'm not wrong, there was two ideas behind going to distributed instead of one single controller. That was fault tolerance and scalability. So as I will solve the scalability.
So as I'll show you, it actually gives you better scalability than user consensus does.
Yeah, so I mean, the main justifiable reason I think for multiple controllers is precisely that, which is that if your network state is so large that it won't fit in one server, then you're sort of screwed. You either need to go to a bigger server like Big Iron, but even then you may have run into either nasty limits of the server itself, or it just becomes sort of overly expensive.
So,
whereas it's much more cost effective to have a cluster of smaller, cheaper servers than one Big Iron when your state doesn't fit.
So let me put it this way. Consensus does not give you scalability in terms of time. It might give you memory scalability, but I can get memory scalability here too. Just put a bunch of, just put. So at the end of the day, if you're just looking for that, then if you can design a mechanism where you put in a second level where you again short out the data and you get that. Consensus, any time you start using consensus, which is for example what Onos and Onyx did for splitting out their controllers, there's no performance scalability. I'll show you results at the end that actually show that consensus time here dominates any of the actual network response times that we're seeing for controllers today. So yes, your point is well taken that we are not sharding. We did not consider sharding in this case. We were just considering current things which mostly just have multiple controllers and use consensus, and hence in reality they're mostly only getting fault tolerance for now, which we improve. The performance bit, we have some ideas in the paper for how you use this exact mechanism to get performance, but consensus is ultimately the bottleneck even for performance scaling.
So that's okay. I'm sure you're gonna answer this question.
No, that's fine. Okay, cool.
Yeah, I just want to reiterate how important I think that is, that the only sane reason for doing distributed controllers is when your state doesn't fit in memory. Because otherwise you could just have a hot standby, basically.
So I'm willing to take this offline, but I know both Onyx and Onos this is not the case.
Well, I mean, as somebody who worked on Onos, that's my take on it.
You have a centralized graph database. Yes, you partition where the graph is stored. Memory partitioning is different from partitioning out so you could still apply memory partitioning with exactly this mechanism. The moment you need to, in fact, this makes it easier because you do not need to get consistency across your memory partitions immediately. So yes, if we can take this discussion offline, I would still disagree that Onos does somehow gives you better sharding than this. We can, yeah.
You consider like making a great path reforming with an architecture like this, where we want to do something that's sequenced
Yes.
properly.
Yes,
and it seems like both controllers are computing the same thing, but following the forwarding tables at different times. In order to do a network thing, you're going to run into some problems.
So that's a great question. Yes, we have considered it. It is, the answer to that is in the paper, but let me just give you a brief overview. The problem is, at the end of the day, the controllers do not have any consistency guarantees on when a table becomes a table is applied on a switch. This has nothing to do with us. This is true for all controllers. The way that people have solved this in the past is by developing these data path consistency mechanisms where you label packets to say, and you label rules to say, hey, this rule only applies to packets carrying this label, and you install the entire set of rules at the core of the network, and then at the edge you flip how you label packets. That same mechanism can work here, and we have an example of how to make it work in the paper if you want to look at that. Okay, so that was, as I said, mostly the idea. But there were a few questions that kept coming up, which is, how does one write control applications in this world? How does one support existing event-based algorithms in this world? So, what about all of the POCs and NOCs and ONOS control applications that exist today? The question which I guess you were sort of hinting at, which is, how do you is it efficient, given that we're constantly sending all of the network state around? This is the question you asked, which is, what happens if your path properties or other things that cannot be violated, or you want to do make before you break style things, and how to safely update network policies. So, that's the final one, sorry, I forgot. And finally, this is the caveat: there are policies that cannot be implemented with this. Means there's no magic here. The lack of consistency does reduce the capabilities of the system as a whole. I'm not going to talk about any of these three, but it was at NSEI 2017. If you go read the paper, it does actually walk through proofs for all of these, and there are proofs for all of the claims that are made in these slides. I'm just not going to talk about them. So, okay, so this is what SCL looks like. We basically have the controllers and the switches. As before, we added two little pieces. We added a proxy and an agent. Proxy lives by the controller. Agent lives by the switch. Please try and remember this, because with very high probability, I will forget and confuse. Okay, so for our implementation, we just used POCs. We built on it because, I don't know, it's from Berkeley. It was easier to do. I don't care about Python that much. Anyways, we have switch agents which implement querying and channels. So if you think about about open flow switches from at least like a couple of years ago, this is equivalent to we change OF agent on many of those switches to add some additional functionality there. We have controller proxies which are responsible for ensuring data convergence. So all of the consistency logic and all of the eventuality logic lives within the proxy. And we place some requirements on the applications that run on top of these proxies. So the first one, which I have mentioned a couple of times already, we need them to be deterministic. There isn't a particularly good way around this, just need determinism. We require idempotency, so we want it to be fine if you apply the same rule multiple times on the switches. And this is actually not that hard to implement, especially if you can consider any memory on the agent, or if you consider that applying to this, writing the same rule to the ASIC twice is fine. For this paper, explicitly assumed only proactive SDN applications. So we're not looking at applications which send packets up at the beginning of a flow. The way I would say this is, we basically are designing for environments where there are relatively few dynamics in the system. We can handle cases where there are lots of dynamics, but that's not what we are optimized for.
So with the idempotency, there won't be a rule that will be dependent on some counters.
No.
The statistics of the switch.
Yeah.
Can't.
No, I do not. Well, it depends. So if it's a rule that says conditionally, if this counter is over this, is greater than this value, do block. And that's the exact rule you're sending now, that's fine by us. If you have a rule of the form based on the current counter value, here's you'll come up with different rules, that might be problematic. So let's briefly look at how proxies work. So proxies have a few different things. They maintain a log of all prior network events, and we basically allow this. This log is not guaranteed to be stable. This log is constantly changing potentially. All switch events are received by the proxy. And every time the proxy receives a switch event, it immediately asks the application to process it. So this is very much like what current SDN controllers look like. And the computation that the application performs is always based on the current log. And the only requirement here is that, let me walk through this and then I'll tell you. Whenever the controller comes up with a new update, it sends it to the proxy. And the proxy also maintains some state about what rules it has installed on each of the switches. And it deduplicates updates. So if it happens to know that that the switch currently already has a rule in place and that rule hasn't changed, it will not send the update. And this happens to be safe in this case because we do periodically go and ask the switch, hey, what is your current, what are the current set of rules that you have, and resynchronize. So it works out fine in this case. This is actually not that different from what the OVSDP protocol looks like, except not distributed in their case. And using those mechanisms, we want to get a few properties. So the first one is we want to get agreement. So all proxies, so we remember proxies are by the controllers. All proxies must eventually agree on the order in which network events happen. They must also agree on the set of network events. So in this particular case, one of the ways we weaken the system is we do not assume TCP. So events are allowed to be lost, controllers are allowed to go away for arbitrary amounts of time. But despite this, we want to make sure that all controllers eventually agree on the set of events that happen in the network. And finally, we require this awareness property, which is eventually, assuming quiescence, the controller and the network will always agree on the state of the network. So the controller will always find out that certain link is up or down. There won't be a point where for infinite time the controller is unaware that the link is up or down. Okay, so to address this, we rely on a couple of mechanisms. So the first one is we have the proxies gossip with each other. So they send messages to each other saying, hey, these are all the events I've logged, and this is the order in which I've gotten these events. This allows us to get eventual agreement on these messages. Part of this is we have a canonical way in which messages should be ordered, and whenever two of these controllers disagree on event ordering, they use that canonical ordering mechanism to get a single order that they can both agree on. But this also makes sure that any observed events are always seen by all controllers. So you can, if a controller misses an event by gossiping with other controllers, it will get those events eventually. The second bit, as I said, is we periodically query the network for state. We ask the agent to send us state, and this allows us to get both routing tables and link states from there. Okay, so that's basically the end of that part. So now to sort of go into this more into this weirder question about why should we abandon consensus? Are we giving up on things, etc., etc.? So the reality of this is this. Look, every time people say, hey, my controller state is what I'm going to partition and operate on, you're sort of making this weird assumption that the reality about what is true about the network is known to the controllers and not to the network itself. In reality, the state of the controller doesn't matter. It's just a reflection on what the network was like a few microseconds or a few nanoseconds ago. It's not anything more important than that. And the truth about the network actually lies within the network. It doesn't matter how firmly a controller or an operator believes that a link is up. If the link is down, the link is down. It doesn't matter what the network believes. What the controller believes. And in reality, and this is just because packets are being processed by the data path. Ultimately, what the packet experiences is what the data path has, not what the controller has. So in reality, removing consensus is completely fine. We don't need to make any assumption about stability of state in the controller. But then to the second point, it actually helps us improve performance. So if you look at responsiveness, which is how quickly can controllers send back values, like ultimately one of the main points of having controllers or having controllers respond quickly is we want our network to recover very quickly from any changes. If you look at consensus, it takes at least one RTT where the controllers need to, or all the consensus participants need to talk to each other and reach consensus. In SCL, because there is no synchronization between the controllers when responding to an event, synchronization only happens eventually, you can respond immediately to any event. And again, this is not useful when your network has lots of dynamics going on, but when your network is mostly stable with one link failure, one link up, this actually means that you respond very quickly. Yeah, question? We already sort of talked about the scalability problem. You have an increase in latency with participants. Here, actually, the time taken to respond to any event is completely independent of how many controllers you plug in or what you do. And fault tolerance, this is again an obvious one. You don't need a quorum anymore. We're not requiring that. Yes.
This is scalability in the controllers, and what about in the network sense?
What about in the network sense?
Yeah.
So yes, you are correct that as the network grows in size, this becomes unscalable because the amount of state that we are synchronizing might potentially grow.
Yeah, there's also this throughput thing, right? You talk about latency, we all like low latency, but sometimes we also care about.
Only 5 minutes, I will respond to that question. I have some.
Well, it's just not on your chart.
No, I understand, but I will respond to that. To your point, yes, you're right. So the thing is, in reality, what we actually ended up doing was we have a set of mechanisms on the agent and the proxy that really do try to reduce the total number of messages, or the total amount of data sent during each synchronization phase to exactly the same amount that would be sent if you were sending out messages. The particular thing that we do is we have the controller send down something saying, hey, here is some hash or proof of my beliefs about you. Please respond if and only if you think this is wrong.
I see. So you're okay. I see.
So you can suppress a whole bunch of messages that way. And I will talk about this in a bit. This idea that once you're willing to give up on consistency here and you're willing to reason with things eventually becoming correct, you can use other mechanisms to really reduce your data throughput. I will talk about it in a bit. And we've been looking at some of these mechanisms now.
So there's an alternative to all consensus and replicated state machine that is primary backup.
Sure.
And why not going that way? What makes networking work so pessimistic that this can work?
And this is kind of what you're doing anyway, because all controllers see all events.
But it's primary.
There's no partition.
There's no partition.
Except that it's not consistent, right? With it. So primary backup should be consistent, right? This is just eventually consistent primary backup, as far as I can tell.
You're not doing any kind of partitioning. Basically, everybody's looking at the whole.
But that's the point. I mean, it's very much. I mean, all is. If I understand you correctly, all your controllers are basically backups of each other or alternates, right? You can click one and another one can just take over.
So the reason I'm saying it's not primary backup and it's primary, it's not hot standby. It is really
it's eventually consistent.
No, it's not just that it's eventually consistent. All controllers are active all the time. So your question is this is not primary backup. So we're not doing failover to a backup. We're actually all controllers are always active. They're not hot standbys. They're all primaries in this case. To your
I don't really see a particular.
So if you look at a lot of the fault tolerance literature, primary backup usually means that workloads fail over from the primary to the backup during failures. If you look at a lot of high availability systems that are built today, you don't build it that way because it doesn't work out very well at that point. You just have n things. You load balance your loads across those n things. At which point, all that changes when you have a failure is one of the things gets more load, but in exchange, none of them is a backup. All of them are acting as primaries and constantly servicing traffic. So this is closer to that. We do the equivalent of that. Except in our case, we don't even load balance. All requests are serviced by all controllers at all times.
Which means you sort of lose the advantage, in some sense. But I mean,
I don't quite see.
I think that does answer his question, right?
No. So to your question. So in general, we thought of sharding as an orthogonal step to this. So if you look at something like Hyperflow, for example, it shards, but it relies on different mechanisms for consistency. You could layer this on top of Hyperflow, in which case you would get exactly what you're saying. We would be able to split up the network into various bits. And so we would have shards and we would still have multiple controllers. It's still not quite where you wanted to go, which is to have primary backup. But
what you were, among your talk, you were saying that primary backup doesn't work when a failure happens, and you want to switch from the primary to one of the backups.
It takes a while. It adds latency. So the problem
The RAM cloud backup mechanism can be quite fast.
Okay, so again, RAM cloud runs on one RAM. My question is this: if I have two things that are working, one of them fails, switch time is determined by time it takes to decide that the failure has happened, and then getting things to respond. In this case, there is no switching time. Things respond. The moment something fails, someone else will respond as soon as they get a request. That is why we are going to that. That is why we prefer this going to that.
I think that can be quite fast, especially if you're just talking about controllers and you have a kind of a rack or multiple.
So I think it depends on what your model of this.
But for controllers, I just want to make sure that your concern is the fact that when the primary goes down, it takes time to go to past the primary.
Yes.
I mean, you're already eventually consistent, so there's some kind of lag in the system anyway, right? So do you really care about that? I mean, that is to say, if your recovery time is less than your eventual consistency convergence time, then that would be perfectly adequate, right?
It depends. It depends on the number of network events that are happening. It depends on a variety of other things. At least when we investigated this, so we tried both primary backup and primary. The primary backup recovery time did add significant overheads when we were in a reasonable network with small dynamics. So yes, we found it to matter. Now, in reality, to see whether it matters or not, you need to go run the test and check if it matters. It will depend on your network. For our networks, it mattered.
So I think I got lost here.
Sure.
So if this performance is about, what performance about?
Okay. Performance is about if you start failing things, how long does it take for something to, how long is it before things come back?
Okay.
So basically,
so from the failure detection to the failure recovery.
Exactly. Between failure detection and recovery, what is the total amount?
And so in format slides, you said controllers are gossiping each other.
Yes.
Why it can respond immediately?
Because all network events go to all controllers. The reason controllers gossip with each other is just in case one of these events gets lost. So basically, what the failure model that we allow is any controller can disconnect and reconnect whenever it wants. It can completely fail and come back whenever it wants. And in fact, we allow even cases where all controllers fail and come back, which is a particularly weird failure mode if you think about it. And so in that case, if you disappear and come back, or for some reason a message is lost, you gossip to figure out what you've missed or what you might have lost.
That's for network policy?
No, that's for network state. Network policy, we assume, is consistently and updated at all controller levels.
Why can't you just get a snapshot from the network when you come back from failure?
So you also need people to agree on ordering. The network does not have any ordering information. The controllers are the ones, the proxies are the ones who decide on the canonical ordering of events. If you just query the network, you will get the set of events, you won't get the sequence of events. Ultimately, what we present to the application is a sequence of events.
But presumably, you use the same mechanism for local sequencing, like vector clocks or something, so that anything from a particular switch is all ordered nicely. It's just the inter-device or global ordering is the thing that you worry about.
Yes, we do assume.
Although in some sense you don't worry about it because you're not strictly consistent anymore. So
no, we do guarantee eventually that all controllers will agree on the order in which events happened across the network. So yes, we do care about it. Okay.
Sorry, that's not what I meant. I just wasn't clear about it.
The basic point. So these two graphs are trying to show convergence time. So these are in simulation with particular late latencies. But the basic point is that in both an AS where, as you said, there is less link diversity, and in factory where there is significantly more link diversity, in both cases we actually find that not waiting for consensus, not having to wait for everyone to communicate with each other, and having the nearest controller be able to respond to any event does actually help us with the latency to respond. So one thing that you brought up that is a good point is that in all of these graphs that I show, we assume a pretty good distribution of controllers. So rather than assuming that controllers are centralized in one place or are close to each other, we actually want our controllers to be maximally spread apart in the network. And that's exactly the model that this one is, these graphs are using. So it's not a model where controllers are next to each other, responding to each other.
So you were also talking about the quiescence property.
Yeah.
What is the time? Can you give us some number of like
okay,
times?
So one of the things so there's a study from Microsoft by Philippa Gill, who's now at Stony Brook, which came out, which came out about in 2011 or 10, and she had this number that within Microsoft they see link failures every 5 minutes, but the chances of seeing multiple link failures simultaneously is very low. And we, in this particular case, to draw these CDS to see what was happening, we basically took her distribution of failures, sped it up by 10x to just simulate a worse behavior, and drew failure rate from that.
So,
a link was failing approximately every
So in your picture on the factory,
yes.
Presumably you said the controllers are maximally distributed, but
yes.
you're still within a data center, right?
Yes, within the data center, but like they're on different racks. So we assume like 3 controllers for this.
But you're still seeing like 3 to 4 seconds.
No, this is milliseconds.
Oh, milliseconds. Sorry.
Sorry, I definitely different axes. My sorry. Okay. And this is trying to quantify the agreement phase. So when is everyone aware of everything? When do they all agree on their thing? So again, the main gap here comes from the fact that again, this was run on a network with an in-band network. In an in-band network, the queue buildups on the control channel will, in the worst case, cause you to So we here for consensus we define agreement as when a consensus round has finished. For SCL we define when all of them have the same log. So that gap again comes from waiting for the act from the consensus round. Actually, again, the numbers are better, but the tail is longer.
What is the step there?
So I actually have forgotten. I can look it up again. I had an explanation for what it was. I did not write notes to myself because I was stupid, and I don't remember it.
It sounds like something that both the schemes.
Yeah. Yeah, so there's probably like some, so for example, here one likelihood is that for this particular ACE topology, which is a topology I've used many times before, it looks like a dumbbell topology. So there is a single link connecting to two richer trees over there. So it might be for cases where either there is queue build up there or there is something that's slowing that down, but I'm not sure. Okay, there's a whole bunch of other work in the paper, which, if you're interested, might be interesting to look at. As I said, most of this was done in simulation. This is not one of the cases where we built the system. We were just trying to look at this. In terms of related work, so as I said, there's been a bunch of work on control plane consistency, and this includes, of course, things like ONNX and ONOS. But also, like, if you look in the last year, there's been, or 2 years ago, I guess, there's been this work. So OpenFlow started supporting atomic registers as a primitive in a newer version, because magic. And there's been some work from Stefan's group over in Denmark about using those atomic registers to implement consistency for controllers. Now, what actually got us started was some work that came out of Princeton in 2015, where they said, well, like this consensus thing not strong enough. People might process the same event 20 times. Let us get to exactly one semantics. And so this is some work called Robin. And then there's been a bunch of other work on data plane consistency. This includes work from Wright-Blatt et al. From 2012. They actually have this great paper title, Consistent Updates You Can Believe In. and other things around that. And recently, there's been some work at looking at PTP synchronization and clock synchronization to get consistency there. Okay, I think I'm out of time, so I'll end here. I have some weird slides about what I'm doing now, but let's not worry about it. Okay, so in conclusion, right? So the conventional wisdom so far, at least, is that the distributed SDN controllers need consensus. In this talk, what I was trying to convince you was that no consensus is required, and you can use existing single image controllers with things like SCL. And this has a bunch of implications, including it simplifies controller design. You don't need to go pick graph. You don't need to go switch between 5 different consensus implementations as you try to decide which is fast enough for you. And it improves convergence time, responsiveness, and robustness for these controllers. And that's it. Thanks. Sorry for keeping you 5 minutes longer than originally intended. Yes.
So you mentioned you were going to talk about a little bit about make before break and about not pushing.
No, I wasn't going to talk about make before break. Make before break is in the paper, but I have no slides on it right now.
Oh, okay.
But it's basically using data plane consistency mechanisms to make that happen.
Yeah, because one potential issue is that one thing that I think drives people down the consistent routing road of don't push a route before you really know it's the right thing is the sort of concern for things like security, where you don't want to momentarily open up sort of unauthorized paths in the network. And so what that means is that it sort of doesn't matter. You're going to have to wait until your eventually consistency actually hits consistency, or you'll have to do consensus.
So
it wouldn't really be safe to
several years ago, Colin and I wrote this paper called Cap for Networks, and in which called Cap for Networks, in which one of the things we talked about is unless you're at the edge and you have some very strong information about the computer that is sending stuff, implementing security within the network using OpenFlow doesn't work. You can use whatever consensus mechanism you want on the controllers. We basically have an example where with a single controller, we show you that you can violate security rules there. Security at the edge does not, so this thing does not address things like if you put your firewall at the edge, or if you do what every cloud provider today does and put it on the vSwitch, and you happen to know exactly who's sending a packet because you're on that first hop, you're completely aware of bindings between entities and addresses. Implementing it there makes perfect sense. Yes, we do not address security in this thing, but the thing is, so data plane consistency makes sure that you can guarantee that you switch between completely determined paths. You never switch between a path that takes you through a wrong place. It does not work for access control in this case, but the argument from that paper was access control doesn't work out with OpenFlow anyways, in the way people think about it.
I heard you say 2 things. One is that access control can work at the edge, and the other that it can't.
No, access control works at the edge. It doesn't work, but it only works at the edge when you because the edge has strong bindings between addresses and entities. Entity address bindings cannot be strongly consistent even with consensus when you're programming a private network. So we don't think we're taking away any security guarantees beyond what is there even today.
So if you're operating in a network where things are relatively stable, like the perspective, then the solution seems to work well, based on what you said. But in the cases where it is very dynamic, it seems to fail.
Why?
Well, because you need some kind of consensus to figure out the policies. Is that what you're?
No, policies are stable. You just will eventually decide on what the network state is. So what links are active and what links are dead. So when I say dynamism, I just meant dynamism in terms of network state. If you were doing dynamism in terms of policy, yes, this mechanism is fine. Don't do that. Okay. Don't use this mechanism in that case.
I see.
It's not a universal mechanism.
So if there's dynamism in the network state, you do need some sort of consensus.
No, this will get you eventual consistency. And in our experiments, we found that this works better than others. But one of the things we're working on now is this notion of thinking of network control as distributed state. In which case, if you want to think of these as being inconsistent, and you can, instead of responding to individual events, actually start aggregating events together and synchronize. So as a controller, I can synchronize network state only when I'm done processing the last set of network state. So rather than the current thing where you have a whole bunch of events that are queued up that you're responding to slowly, you can actually snapshot and only respond to the ones which respond to current things. So there actually this is not something that SCL did. We just think the SCL ideas enable that sort of model. Yeah.
So can you talk a little bit more about sort of, I guess, reactive applications and scalability?
Do not support reactive applications, so that is the last bit about that. Just don't support it. Scalability, do the same thing that Hyperflow does or B4 does. So break into regions and.
Yeah. So you seem to indicate there's a trade-off there that once you shard things, then your recovery becomes local.
Yes. But I don't know how bad that is. Like I haven't done any experiments on this.
So is it fair to say that like reactive applications in your context would just be applications that can feed in your network policy? You have some
Yeah, basically.
So like a BGP speaker or something.
Yeah.
A reactive application. You receive that face
And so basically the assumption is that we want the reaction times to be relatively rare. So BGP, this is fine, right? BGP updates are anyways happening at minute orders, or at order minutes, that's fine. For something like flow arrival, that's not good for us.
Sort of press on consistency a little bit, the opposite of what I was saying. Well, for security, maybe we want real consistency, but it seems that, in my experience looking inside the switch, everything's eventually consistent anyway. And if you look at the way networks actually operate, they're all eventually consistent anyway.
Sure.
So is the purpose, I mean, are we maybe doing the wrong thing going for this kind of replicated state machine model where everybody has to have a state machine that operates in lockstep based on a globally consistent ordering events and everything's, when really we could just kind of eventually.
Yes. In 2011, when I started grad school, I had never heard of networking. I thought networking was something weird used it. And one of the first classes I took, I was sitting with Justine, and Justine told me that, hey, networks are moving towards having consistent things. And I said, you people are crazy insane. What sort of idiots would do that? Of course, self-stabilizing is the way that everyone should always have been designing networks, and that's how we've designed networks so far. What are these idiots thinking? I would roughly stand by that mechanism, to that statement even today, except, of course, designing self-stabilizing algorithms is hard. Designing super stabilizing algorithms is even harder. And some of the policies that we are starting to get to don't work with just self-stabilization. They require the super stabilization bits of it. So I think we went down the path of consistency because it was just easier for people to think about. And this is always the trade-off that people don't want to talk about it. It's really easy to sit around and say, hey, assuming someone is perfectly smart and knows everything perfectly well, they could use any system to build anything. Most engineers, and I would put myself in this camp, aren't those people. So we need tools to actually help us do this. And the reason we went down the RSM way was it was a tool. And what I'm saying here is that if you remove that tool, you can still build similar to what you were building, how you were building RSM-based applications, and still get all the benefits, and you can still abstractly think of it as the same exact problem.